Do you hear? Yes. Do you hear? Can you hear me?
I hear you, yes. I hear you, yeah.
I see that you've made to EthCC. If you remember, I asked you in DevCon to come to EthCC, and you still made it. Thanks.
Wait, sorry, I didn't quite catch that last bit.
Yeah, I asked you to come to EthCC in Osaka at DevCon, and I see that you made it. So thanks.
Thank you. I appreciate it.
Yeah.
Okay, you can start if you want.
I can start, you say?
Yep.
All right. Well, give me one moment. Oh, I just realized I need to provide system preferences. I'm so sorry.
It's okay.
For my sharing screen. I will be right back.
Yes.
And we are good. Full screen if possible. That's okay. All right. Well, welcome everyone. It is currently 3:58 a.m. So I empathize with anyone who is tired in the morning. I unfortunately can't see who is here. However, I will be able to see your questions, and I would love to see that you are here, because I don't want to necessarily just give a presentation where this could be a YouTube video. So please, if you go to slido.com and you type in Y231, a great code there, you can ask questions. And so I will be, oh, perfect, hallelujah, hello, I saw anonymous hello. So please say hi, tell me how your day is, and also just ask questions and stop me basically wherever. So let us begin. Today I'm going to be talking about the optimistic virtual machine, optimistic rollup, layer 2, and a lot of really fun stuff. And I have an insane number of slides. I in fact have something like 600 slides, so I don't know if I'm going to get through everything, but nonetheless. The dream, right? We have this dream of taking cryptography, economics, combining it and giving us all superpowers, the ability to, use crypto economics to build these new incentive structures, these new applications that we haven't seen before. And this dream has, excited me for many years. And, ever since I saw DevCon 0 videos on YouTube. Though it has been, a real thing to work for. And of course, unfortunately, we're not quite there yet, and we're not quite there yet for the most mundane reasons in the universe. At least one part of it, right? We have these transactions that have massively complicated information, in these, and we approve transfers with infinite coins, and I try to send these transactions, and the speed up button, I click the speed up button on MetaMask over and over again, and it still doesn't get faster, doesn't get fast enough. So there's just like these fundamental, pretty mundane problems that kind of hold us back from a user experience perspective, from the scalability, the actual cost of all of these transactions, the speed at which we confirm all of our transactions, even things like who's paying the gas fees and stuff. And, I don't want to be paying 30 cents, unfortunately, for all of my transactions. And so we actually, these problems are so apparent, the potential is so clear, but we still have, a little bit of a ways to go. Great, I got a bunch of people saying hi. Well, hello, everyone. Great. But anyway, so we realized I'm going to kind of give a little bit of a story back maybe about a year ago, not a year ago, this summer, a little bit, like actually, yeah, almost a year ago, when we were kind of looking into this kind of conception of layer 2. So I work on a lot of layer 2 stuff. I was working on Ethereum 2, I was working on Casper, and now focusing on building out, Ethereum scalability inside of layer 2. And so basically, if we go back to probably basically last summer, we were thinking about, and by we I mean Optimism in particular, Ben Jones and myself and a number of others, Vitalik, etc. And we were talking about these optimistic futures cones. And so I'm not really going to go into it, but basically we realized that if you take the normal, EVM state machine blockchain and you apply this optimistic layer on top of it, then you're kind of, you can actually, what you can do is you can operate on optimistic states. And so that means that off-chain information, so Alice sending a transaction to Bob off-chain, we can actually take that transaction and optimistically calculate future states of Ethereum and essentially do computations on what Ethereum will be. It was this kind of like weird mindset shift that like really exemplified what it is to be, layer 2, and and this is something that actually held for all of these different layer 2 protocols. And so we kind of like, we're looking into this and getting these like research epiphanies and realizing that optimistic states were based on off-chain data and on-chain data, and that all of this data is really, follows the same format. And so these epiphanies kind of led to a consolidation of all these, layer 2 protocols, even layer 1 protocols that we realized were like really not so different, right? And they were unifying frameworks. And so this was kind of the beginnings of this like, layer ridiculous optimistic meme. But nonetheless, we realized that Ethereum really has we can really use all of layer 2 to make Ethereum better. And so, whenever I have an excuse to put an Ethereum logo on a bunch of hearts, I do it. So I did it there. Anyway, so now I'm just here and I can say questions, although this part, that's kind of just an intro. So, right, we have this problem. We clearly need, scalability. We need this instant transactions. And we also have this layer 2 technology, which is kind of fundamental, and the barriers between all of the layer 2s are not so different. So now I've said that the barriers are not so different, but let's actually go into the kind of different layer 2, the kind of meat and potatoes. This is for someone who really wants to understand, like, okay, what is the layer 2 space at a high level? What does it look like? And so I'm going to give you, this is a lot of layer 2, goodies. So layer 2 blockchains all form the same kind of structure. And I'm talking about, rollups, plasma, state channels, etc. They all have this kind of, they're all these state machines. They have states. These states accept transactions, that transitions it to another state, which has another transaction, transitions it to another state. And there's important properties that must hold for these layer 2 state machines. First, oh, and by the way, this of course is the, head state. And so all of these layer 2 state machines, they have their state roots or, state commitments, information about the current state of this state machine is sent to layer 1. So layer 1 has an idea of what is going on in layer 2. And in particular, the 2 guarantees that it really needs is it needs to know that, one, that this is the most recent valid state, right? So all of these state transitions are green, meaning that these are, valid state transitions. And additionally, we need to know that the users who are interested in downloading the state will be able to download at the very minimum the head state of this layer 2 state machine. So these are two of the most important things that these layer 2 state machines must provide, and that is validity, which is the state transitions are valid, and availability, and that is the ability to download the actual head state. And so our layer 1 needs to understand, our like parent, our layer one needs to understand the current state of the world in terms of what users can download and what is actually valid without having verified or computed all of the layer 2 state transitions directly on layer 1. And so it's this kind of resource constrained state machine because in fact, of course, layer 1 itself can also be represented as a state machine. And it's a kind of global view of the entire world. And so you can actually have multiple of these state machines at different stages with different states and different transition rules. And so you're committing all of these to layer 1. And in fact, you can even have, nested state machines where you have one inside of another. And in fact, this is not, this is actually not crazy. It is, you can think of it almost, you could even think of it as a, this is a shard and this is a, plasma chain on top of that shard, or maybe this is a roll up and that's a plasma chain on the rollup, or a rollup and a rollup. It's all good. And so if you don't understand rollups, I am assuming some knowledge of layer 2, but I'll do my best to define those terms. So all of these use limited compute and memory on layer 1. And then as we go from this, layer 1 state machine, we actually get less and less compute and memory constrained. And of course, the kind of trade-offs here we make are dependent on our layer 2 protocol. And there's a number of different layer 2 protocols. So for instance, optimistic rollup, that's the thing that I'm going to be talking about mostly. ZK rollup, plasma, state channels, etc. These are all examples of these kind of layer 2 state machines. And that's really like what we are talking about. When we're saying we're going to scale blockchains, we're going to scale this trusted state machine, well, we're going to scale it by making these sub-state machines inside of it that we preserve properties of. And so users can download everyone syncs the main chain, whether that's ETH1 or the beacon chain, and then users can download the head state of whatever the sub-state machine that they actually care about. So the important kind of scalability aspect here is that user A is only downloading this kind of layer 1, as well as the optimistic rollup chain or the shard or whatever that they actually are interested in. But what are the differences between all of these different layer 2 protocols, right? That's the commonality, but what are all of the differences? Great. Cooperative environments, so does this work? So I just saw a question, and so now I have to understand how to keep going without even though I want to answer the questions. I'm going to answer a bunch of questions in just a moment. But anyway, so comparison of layer 2 chains. So we have this optimistic rollup, ZK rollup, optimistic plasma, ZK plasma state channels, etc. So first, all of these must have a liveness mechanism. So I talked about availability and validity, but the last component is liveness. And so liveness is just that all of these state machines, they actually must be able to continue. But this is kind of one of the ones that is shared across all of these layer 2 protocols. They all have a kind of similar mechanism that can preserve liveness. And the reason why liveness and validity and availability are kind of 3 good distinctions. I won't go into entirely, but basically we need the guarantee that we can download a valid head state and we can also progress it. And so what we can do is we can say, okay, let's use forced transactions. It's pretty simple. So we have a parent, which is L1. We send a transaction on layer 1, and that forces a state transition on layer 1, which then forces a state transition on the kind of child chain. So that's just, to be complete. There's a liveness mechanism for all of these that preserves the liveness property of all of these layer 2s. But I'm not going to talk about that in too much detail because I'm going to focus on the availability and validity mechanism, which are the distinguishing features. So first, rollup. Rollups have all the same availability mechanism. All of the transactions are recorded in order on chain, and this allows you as a full node to compute the head state. So what does that mean? That means that as a user, I am able to download from Ethereum the genesis state, right? Whatever the first state is that this sub-state machine was, started out in, and all the transactions. And I'll use that to compute locally, off-chain, whatever, on my computer, the current head state. And then then I can create the head state. And there's a validity mechanism. So the thing that distinguishes optimistic rollup and ZK rollup is the validity mechanism. And so we need the ability to have Ethereum know that this is not only the most the valid, like a valid available state, but we also need to make sure that it is a valid state. And so there are two ways to do this. The first way is fraud proof. So that is the kind of optimistic rollup. And so the way that we do this is we periodically commit to state roots. Every state transition, we're committing to that state root. And if there's ever an invalid state root committed on chain, then what we do is we expect one user to just say, okay, I will challenge that state root and I will prove unequivocally that this previous state and that transaction and this post state are, and this results in a different post state. And so with that, I can actually just delete this invalid post state and roll back to the most recent valid, state root. And so this is essentially, we can use this fraud proof to say, okay, I'm just going to prove that something went wrong. And if the thing went wrong, then we delete whatever the invalidity was. And so this is how we can preserve our validity. However, it does come at a cost because it does impose a delay because you need to give users the ability to post these fraud proofs. Now, the second way is succinct proofs. So ZK rollup or zero knowledge proofs, right? This is snarks, starks, etc. And in this, we can actually just prove up front that our transactions are valid. So we have our states, our transactions, and we just straight up prove the state transitions. We're able to do this succinctly, so we can, the layer one knows precisely the moment that it is committed that everything is valid, or the snark is, there's some bug in the snark or the smart contract. So that is optimistic rollup and ZK rollup. The next two are optimistic plasma and ZK plasma. So in Plasma, it has a different availability mechanism. So it still guarantees availability of the head state. However, what it does is it uses an availability challenge when the head state is unavailable. So essentially what you do is you say, hey, Ethereum, make the head state available. And with that, Ethereum will play this, what we, is commonly called it like an exit game, which will reveal what the head state is, the most recent valid and available head state. And it will, reveal that to the user and allow the user to mutate that head state in whatever way it wants using a forced transaction, which is essentially an exit. And so this has an implication, which is very interesting. And that is that if the state were to spontaneously become unavailable because the operator went offline or whatnot, and committed a state root but didn't provide any witnesses, then the head state might be unknown. And this is a real problem because, for instance, if I'm trying to interact with a smart contract and I don't know the current state of the smart contract, I won't necessarily know what to do when there's a liquidation event or any other kind of problem that might occur. And so this actually just changes the use cases for Plasma because it makes it harder to build an application if your state can eventually for one challenge period become unavailable. It's still very useful, but it's very useful in certain use cases. And so the use cases are also different for state channels. They're very useful, but it has a bounded participant set. State channels are basically like the most amazing, but they have a bounded participant set, which makes them limited. And so this is a kind of overall picture of all of these different layer twos. And I'm going to take a peek into all of the questions to see if there's anything I can answer. So for rollups, when you say recorded transaction on chain, are you talking of the L2 chain or the L1 chain? Both are possible, but with very different trade-offs. Very interesting. Okay, so what I mean really is interestingly enough, if I'm talking about rollup and I say it's recorded on chain, I essentially mean that there exists some oracle on chain that is saying this transaction is available for download. And so realistically, that means in like practical terms, that means submitting it to like Ethereum 1, putting it through call data, making it available. And then you know that it's been propagated by the Ethereum network. So that's how you do it in Ethereum 1. In Ethereum 2, you submit it to a shard chain, and the shard chain, there's some you get signatures saying that this is actually available and included in a block. And so there are different ways to prove this, but they all boil down to like an availability kind of certificate where you know that this is actually available for download. Yeah, so that is that one. And there, I did get another question, which is, when will I be able to move my generic smart contract-based apps to a layer 2 chain? And that is very, very soon. And in fact, you can already start messing around with the OVM, which I'm gonna talk about. So anyway, but I'll get to that. Okay, so there's actually another kind of rollup, but this rollup uses a different validity mechanism, and that is actually L1, but I won't talk about that here, but it's just for completeness sake. So wait a minute, what are those issues again, right? We just like went this very high level over all of layer 2, and it's a little overwhelming probably. And we're really all we're trying to do is not just like figure out the kind of fundamental properties of the universe, even though that's very interesting to me. We're also just trying to speed up Ethereum. And so to do that, we need to speed up the EVM. We need to speed up our smart contracts. We need to get our, we don't want to change the developer experience just because we're in layer 2. We want to move all of the amazing work that people have done on Ethereum and put that into a more scalable environment without sacrificing things like security and the properties that we like about Ethereum. And so we want these smart contracts. And so now the question is like, okay, if we want Ethereum in layer 2 in a scalable setting, how do we actually achieve that with all of our different possible layer 2s? Well, first, state channels don't support an unbounded participant set. This changes the kind of smart contracts that you are able to write in a state channel. Because for instance, if I deploy a Uniswap smart contract, anyone in the world can interact with it. So that doesn't quite give us the properties of Ethereum. So the next thing is unfortunately, zero knowledge proof technology is not advanced enough to support the EVM yet. There is a lot of promising, work being done on, Planks. And so that is, it seems like VMs are coming soon. And I'm very excited for that. But it is not here yet. And so I have waited too long for scaling Ethereum. And so I'm too late, I'm too impatient to wait for that. So unfortunately, that rules out zero knowledge, ZK Rollup, ZK Plasma for now. So now we're left with optimistic Rollup and optimistic Plasma. Right, but remember, we talked about these sudden liveness failures, these sudden, going offline, and no one knows what the actual state is. And so that makes Plasma a little bit, it doesn't really preserve the same smart contract properties that we know and love about Ethereum. So that unfortunately eliminated optimistic Plasma. And so we were left with optimistic Rollup. An optimistic Rollup is great. It's, it gets you, 10 to 100 times the, transactions per second on ETH1, and then, 100,000 times the transactions on ETH2. Who knows? Caveat, and these numbers don't make sense, but it's not as good as Plasma, which is like ridiculous, but it is very nice, and it gets you the properties that we're looking for. And so hooray, we can do this. So we talked about optimistic rollup in L2, and in particular we implemented a first version. And so the thing that of course, Unipig, we buy and sell Uni, and the important thing was that the user experience was actually kind of nice, and the transaction confirmations were pretty fast. So that is the overview and starting to bridge into optimistic rollup and the OVM. I'm going to take one more look at the questions to see if I have missed anything. Nope, I think we're looking good. These slides are online, and I will post them. I haven't created a link yet, but I absolutely will. So That was layer 2 blockchains. Now, optimistic rollup overview. So I'll probably go relatively. Actually, I'm curious in the questions here, if folks, how much of an in-depth you ask all of your optimistic rollup questions, and I will answer them. I'm going to go relatively quickly, but hopefully it's still useful. So we have our Ethereum chain, right? And we have our rollup contract. And this is the general form. And this is honestly the general form of a lot of layer 2s, as we have kind of talked about. And so we deploy our optimistic rollup chain contract to, L1, and that identifies the genesis state of our optimistic rollup chain, right? Now, what we can do is we can have a bunch of aggregators. These aggregators are, they are bonded so that the fraud proofs have some, there's something to lose. You don't want to have an unbonded aggregator or someone submitting a state root, because then, you don't have something to penalize. You need to penalize people for submitting the wrong thing when you use fraud proofs. Unfortunately, it's kind of annoying. Anyway, so what we do is we first started the chain by submitting this rollup contract and adding these aggregators. Now we're going to, quote, enter the chain. So we'll send some ETH deposits to that smart contract. And what that will actually do is that we'll do a forced transaction, which changes the state of the optimistic rollup chain. It's kind of like sending a message into a virtual blockchain that lives inside of Ethereum. And so that will change our ETH to optimistic ETH. Next, what we will do is we will send some transactions. So we just send a transaction to the aggregator or the sequencer. There's way too many names. Also, coordinator, people say. It is absolutely a mess. Operator. But nonetheless, you send it to someone who is creating these blocks, block producer. And what that does is that, of course, updates their balances in the state. And then what we do is we calculate a new state root based on their updated balances. And we commit to both the transaction and the new state root. And we do this for every single transaction. And we can call these transitions. And so then we'll bundle a bunch of transitions into a block. We'll commit that block, and we will actually create a Merkle tree or a concise commitment to all of the transitions. This is a little bit tricky, but we normally what we'll do is we'll have a constant sized state storage for each one of these blocks. So we're submitting a bunch of transitions. It's getting Merkleized into a single state root, and then not a single state root. Sorry. Oh my goodness. Bunch of transitions Merkleized into a single block root, and then we are storing that block root. The lots of gas savings comes from the fact, of course, that we're doing this constant size state storage because we're creating this kind of virtual chain. But the most gas savings are because we're not doing this computation directly on Ethereum, and that gives us scale. As I said, you can implement a not so optimized optimistic rollup and get 5x transactions per second, but 10 to 100 on ETH1 is a pretty reasonable estimate. So we can do this, and we continue to watch the Ethereum chain, and we see and apply all of the transactions that have been submitted to Ethereum in these kind of virtual blocks to our local clients. And so we're kind of syncing this chain. And remember, it's availability and validity that we are trying to preserve. And so on this chain, we might have Uniswap, and users can actually interact with Uniswap. And this is the kind of thing that we did for our demo. And once again, we're committing these state roots, we're submitting these transactions, and we're committing all of these different transitions and building up a chain. And so we, update our balances accordingly. And now, what's going to happen? What's going to happen? We've got an evil aggregator, someone who is ready to commit fraud. Remember, they're bonded, so don't worry. We'll punish them soon. And they will take our normal transaction and replace the recipient with themselves. Very bad. And they will then calculate a new state root with the result of that transaction sent to themselves, right? This is an invalid state transition. This is an invalid transaction, right? Now, an invalid state root is really the most precise and correct way to say it. So all of the users are going to see and apply that transaction locally to their nodes. They will all notice that something went wrong. And then, well, they will submit a fraud proof. And so we challenge these invalid blocks. And so we have our invalid transition, we have our previous state, and we have a bunch of other information, like all of the storage slots that we are, that this transaction is affecting. And so what we're doing is we're essentially creating a little virtual environment for running this particular transaction, this particular state transition. And we will go through this kind of long process of challenging invalid blocks. Notably, the particulars of this, kind of proof of invalidity are not that important, right? In this case, we are simply proving all of the, we are proving everything is the full pre-state. We're applying the transaction and checking the post root. It's the simplest by far, invalidity proof, but there are many. So just as a caveat. So first we verify that these transactions were actually included in the chain. Once we have done that, then we verify that the storage slots were included. And so we provide these Merkle branches for all of the different storage slots, and we're set. And then we apply the invalid transaction. And remember that invalid transaction's touching all of the storage slots that we proved. And we say, oh, as we're applying it, we notice that the signature is invalid. And so, what are we going to do? The block's invalid. And we can simply remove the invalid block and then remove or burn the aggregators, the malicious aggregators bond. And so we have deleted that horrible, horrible block, got rid of that bad aggregator, and continued on great success. And so we just put a blockchain on the blockchain. Very exciting. So I'm going to take a look at all of the questions because folks may have a bunch. What about cost? Great question. Hi, what about costs? Who pays to commit to layer 1? That's a great question. And this actually depends on a lot of kind of configurations, how you build your chain. Probably the easiest way to do this is users will pay the aggregator, and then the aggregator will pay layer 1 gas fees. So it's kind of like these relayer markets, kind of like these, gas station network, kind of situations where you have an entity that is paying layer 1 fees on your behalf and collecting fees inside of that, some other system. And so the system that these optimistic rollup, aggregators / the sequencer is collecting fees in, that is the actual blockchain themselves. So we can, implement, for instance, account abstraction and all of these kind of meta transaction libraries to pay the fees for layer 2. And let's see. Having sent.
Can you hear me?
Yes, I hear you.
Yeah, just to warn you, you have 5 minutes left, please.
Great. Okay, so the big, my goodness, time flies when it's 3:30 a.m. So the big problem with this was that the Unipig transition evaluator was very, very much hard coded. And so we instead of, hard coding some particular, Solidity contract that's for evaluating this transition, we created a general purpose transition evaluator, the UVM. And so what we did was we needed the ability to verify any state transition in a way that is easy to audit and is compatible with all of the developer tooling that we have today, as well as it preserves the account model and Solidity contracts and everything that we know and love about Ethereum. So we wanted the EVM that could execute optimistically and was compatible with all the developer tooling. And so we are, instead of having a state transition that's hard-coded for Uniswap, we have a state transition for the EVM. And so we can take our layer 2 chains and we prove it invalid inside of this UVM. And the reason why U with the umlaut is because it's like OEVM essentially for now, right? This is an optimistic EVM in particular that we implemented. And so there are two types of virtualization: container virtualization and machine virtualization. The OVM is a kind of virtual environment or a container virtualization. And that means that we're actually creating a separate namespace inside of the EVM, which has the nice benefit of running all of the actual opcodes directly inside of the EVM. So we're not actually like, we're not re-implementing the add opcode or anything like that. We are instead just running bare metal EVM. And so we can actually do pretty efficient fraud proofs. And so on the other hand, there's machine virtualization where you actually implement the full EVM inside of the EVM. And that can be, basically it's just more work. And it's easier to potentially, there's a bunch of complexity there. And so you essentially have the EVM, and inside of the EVM, you have an OVM virtual environment. And inside of, you can have multiple of these OVM virtual environments, or you can, nest them arbitrarily, however you might like. So there are three components to this. There's a transpiler, a safety checker, and an execution manager. So the transpiler, the way that this works is we take our EVM bytecode, which has, an S store in it, and we transpile it into a cross-contract call. And so the cross-contract call will do exactly what the S store does, but it does it inside of this virtual environment. And of course, we're adding a bunch of code here, but this is a non-optimized version of what we are trying to do, of course. But this is actually, as it turns out, it's actually not that much more expensive, because a normal S store is about 20,000 gas. This OVM S store that is virtualized with this virtualized storage is about 24,000 gas. And so that's a 24% gas overhead. And it is in fact a 0% gas overhead for state-independent opcodes. So like add or multiply and whatnot. And so we can take our transpiled contract, send it through a safety checker that verifies that all of the different opcodes are actually safe. There have been no problems. And then we add it to our code that is our execution manager. And our execution manager actually holds all of the state and does all of the kind of the storage holds all the storage for all of our smart contracts. And so, for example, what we have is we literally have a function called OVMS store, which takes out this assembly is just it could have been ABI encoded, but it's not. And so it literally takes the storage slot, the storage value, and it stores it. Literally, there's no difference. And so we do this it's very nice to have very little work there. And so we do this for a bunch of different opcodes, right? All of the stateful opcodes, like create, create2, call, static call, we're just simply shimming those particular opcodes. And so our execution manager is kind of doing this fun little thing, holding all these smart contracts. And so we're able to actually kind of fulfill this dream of having a kind of general purpose layer 2 state machine. And so that gives us the ability to build optimistic Rollup and optimistic plasma. Of course, we care about optimistic Rollup, and that's what we are actually building. And we want to build the rest someday. And so with that, I wish that I could talk about all of the public goods, but the most important thing is that we can actually use layer 2 to extract MEV from miners, and in particular, solve the public goods funding problem, but we still need to figure out how to distribute those public goods. So someday, hopefully somebody can help distribute these, help figure out how to distribute these public goods, like Gitcoin grants, Moloch DAO, etc. But we will see. So all of these things, Ethereum, y'all, I wish I could say hi to everybody here, and I'll post all of these slides. And let me take a quick look at the questions. I'm sure I'm out of time in half a second, but nonetheless, that is that. So how can I be sure that my L2 transaction, this is a question. Oh, am I totally out of time? I'll do one question. Yeah. How can we be sure that my L2 transaction will end up in an L2 block in later Ethereum? Great question. So essentially there are different mechanisms where you can allow the person who you send your transaction to will send a signed promise saying, I will include this transaction. And in fact, this is what the state will look like. And so you're able to get this kind of guarantee that either my transaction will go through within some period of time, or I can, sacrifice their bond just in the same way that the people's bonds are sacrificed if they post an invalid state root. And so we are now at the point where we can build a general purpose optimistic rollup that preserves the Ethereum developer tooling without, too much work. So it's very exciting, and we're, let's talk, reach out. Thank you very much.
Going just maybe at noon. Because noon is the first time.